Hi, boys and girls. Today's video deals with the multiplying property of exponents, the product of a power property. So today we're going to be talking about part A. Right? Here we have the vocabulary you're going to be learning: monomial, product of powers property, quotient of powers property, and term. Right? Your I can statement is I can use the laws of exponents to multiply and divide monomials with common bases. Right? On page 13 of your workbook, it tells you that a monomial is a number, variable, or product of a number and one or more variables. For example, 6y to the second is a monomial since it's a product of 6 and y to the second. The expression x plus 3 is not a monomial since it is a sum of two monomials. When addition or subtraction signs separate an algebraic expression into parts, each part is called a term. A monomial only has one term. The expression x plus 3 is a sum of two monomials and is therefore not a monomial itself because it has two terms. Down here with these expressions, let's go ahead and sort these into the appropriate boxes. Now, monomials do not have plus or minus signs. Monomials do not have plus or minus signs. So this x is just a regular variable and it is a monomial, right? 80 is just a number. It's a monomial. This has a minus sign, x squared minus y squared. So this is a binomial and not a monomial. Monomial means one term, binomial means two terms. Okay. 8x is a monomial because it's okay if you have a product or a quotient, then that's fine. It's plus and minus signs that make you not a monomial. And this over here, x plus 5, this has a plus sign, so this is not a monomial. Okay. Next, there's a rule called the product of powers property. That's a lot to say. What it means is if you're multiplying two numbers that have like bases, like for example, this 4 to the second power and 4 to the third power, because the bases are the same, when you multiply these two numbers together, the product of powers property says you can add the exponents. And here's why. 4 to the second power is really just 4 times 4. All right? And then it's being multiplied with 4 to the third power, which would be 4 times 4 times 4. Well, now we see that there are 5 4s, 4 to the fifth power. Basically, because these two were added to these three, and that's where this property comes from. 2 4s are combined with 3 more 4s to give us 5 4s. All righty, moving on. You can also apply this rule to algebraic terms when you have variables instead of letters, okay? Here we have, or variables instead of numbers. Here we have like bases, they're both 2's, so we can add the 3 and the 4 to get 2 to the 7th power. You can also do it with variables. Let's say if you had d to the second times d to the third, that's equal to d to the 5th. 2 d's multiplied with 3 more d's gives you 5 d's. Okay. So here we have example 1. This is on page 15 of your course 3 workbook. And they want you to simplify. Up here they're giving you 5 to the 4th times 5. Now this 5 doesn't have a power. Well, it's important for you to remember that if a number doesn't have a power, it has the power of 1. Oftentimes students will misunderstand and they'll think that the exponent must be a 0. That's not the case. If it doesn't have an exponent, the exponent is 1. So we go ahead and we can add these two exponents together because there are like bases. The bases are both 5. So we have 5 to the 4 plus 1 power, which is 5 to the 5th power. If you want to get really fancy, you can figure out what 5 to the 5th power is equal to, but I normally won't ask you to do that. So down here we have our check, all right? The bases are the same. They're both 4's. So when we do this one, we will do 4 to the 5 plus 3, which is 4 to the 8th power. Okay. Over here, we have 7 to the 4 plus 2 power, which gives us 7 to the 6th. Just an extra example I threw in there. Okay. If the bases are the same and you're multiplying, you just add the exponents. Example 2, they're using variables instead of numbers. Same rule applies though. Here we have c to the third times c to the fifth, which gives us c to the 3 plus 5, which gives us c to the eighth. Down here in the check, we have x to the fourth times x to the sixth, which is x to the 4 plus 6, which is x to the 10th power. One additional example I threw in here. Remember, if a letter doesn't have an exponent, it's a 1. So this would be k to the 5 plus 1, which is k to the 6th power. Now my final example, it's got some stuff going on here. And I don't know about this formatting thing they did here. This is messed up because it should look like this, all right? The formatting was not right on this. But what they're telling you is if you take terms that have a lot of stuff going on in them, like this, 4 times x to the 5th. What this means is -3 times x to the 2nd times 4 times x to the 5th. And because multiplication is commutative, you can rearrange the terms. Just like 2 times 3 and 3 times 2 are the same thing, you can rearrange the factors in this expression. That makes it easier for us. Now we can multiply these two and get -12. And now we're multiplying two variables with like bases, so we can add the exponents. 2 plus 5 is 7. Let's see, got it over here. All right, so 2 more examples of the messy ones. This one is really -2 times a times 3 times a to the 4th. Rearranging, we get -2 times 3 times a times a to the 4th. Remember, a variable with no exponent, the exponent is a 1. Multiply -2 and 3, we get -6. And a to the 1 plus 4 is a to the 5th. Coming over here, looks like D is the winner for this one. And one last example that I made up, and I just threw it in here. I'm going to rearrange this one, -4 times -6 times c to the 2nd times c to the 6th. Well, -4 times -6 is +24, and c to the 2nd times c to the 6th is c to the 8th. And that's my last example in this section. I hope that this helps clarify for you. Good luck on your assignment, and if you have any questions, by all means, come to class and ask them. Thanks.